Hi, welcome back to CVNE305. We were talking about material responses, and just to quickly summarize last class, we saw that there were two major kinds of responses. If you remember, one was has to do with how the material deforms due to the application of forces. One is where when you remove the load, it will come back to its original shape. This is temporary deformation. Persistent deformation means that if you remove the load, it does not come back to its original shape. So these are two rather sharp distinctions, two ends of the spectrum, if you will. If it comes back to its original shape instantly, as soon as you remove the load, it will be termed elastic. I'm saying this in a fairly loose way, but that's the idea. If it does not come back, it is called plastic. And in some cases, it may come back after a long time, then it would be called a viscoelastic solid. If it doesn't come back but it partially recovers, then it would be called an elastoplastic material. So we have seen all the different cases here. And then we looked at what is meant by a linear elastic material, in which case the response between the connection between the stress and strain is a linear relationship. And that is typically the case for metallic materials within about 0.2% strain. What do I mean by 0.2%? Change in length over original length. So delta L. So remember our axial strain which is delta L over L must be less than or equal to 0.002. That's pretty small. That's 0.2%. So for every 100, say 100 mm, it will change by 0.2 millimeters. Makes sense to you? So that's a fairly small deformation, and within that range, it will be linear. Beyond that, different things can happen. For a rubbery material, on the other hand, you can go up to 40% strain and it will still completely recover. Elastic, like an elastic rubber band. Even that, if you do it very fast or if it is very hot or something like that, it may not recover immediately or it may not recover at all. So each of these cases is different. Today we are going to look at linear elastic materials, connection between stresses and strains that are linear. Okay, and we are going to look at what is the situation between how are the stresses and strains related. Okay, so that's where we are headed. So we are talking about what is called Hooke's law. So question number one that we are going to answer is, what is Hooke's law? So Hooke's law says that the relationship between the components of the stress, so let me be very specific, 6 components of the stress and the 6 components of the strain is linear and is represented by a 6 by 6 matrix. What do I mean by that? So let us write it down. So we have response, and then we're going to write stimulus here. Let me write it all the way out here. So stimulus list is on this side. So I can apply a pure normal stress in the x direction, a pure normal stress in the y direction, a pure normal stress in the z direction, a pure shear stress in the x direction. These are the 6 possible inputs I can give. right? And some combination of them. For example, I can give sigma xx, sigma yy, so on. So these three or normal stresses, and these three are shear stresses. The corresponding response could be pure axial strain in the x direction, pure axial strain in the y direction, pure axial strain in the z direction. So that means what used to be a cube like this has become a much bigger cuboid, or maybe a much smaller one, right? Then I could have pure shear strains. So, and the relationship between these two things is represented by a 6 by 6 matrix, and this matrix is called the compliance matrix. This is what Hooke's law talks about. So let us look at some simple experiments and let us see if we can figure it out. So first experiment is a very simple one. I take a sample and I do uniaxial extension. So let us do it this way. So I am applying a force Fx, which is sigma xx times A, sigma yy, all the other things are 0. So I got 0, 0, 0, 0, 0. All of them are 0. So what will happen? Experience suggests, and this is purely empirical. Empirical experience suggests if you do that, it will get longer and thinner. So stimulus and response. Longer and thinner. That is, I will have, if sigma xx is not equal to 0, all others 0. For many materials, you will get epsilon xx greater than 0. So let us make it very clear. Epsilon xx greater than 0, epsilon yy, epsilon zz less than 0. This is what you will get. Okay, typically, not always, typically. So what this means is that first idea is the following: if the response is linear, then for this experiment sigma xx over epsilon xx is called E, which is Young's modulus. Epsilon yy over epsilon xx, negative of that, is called nu. This is pronounced nu, and it's actually the Greek letter for n. So this is called Poisson's ratio. Okay, this technically this should be called, since it is between y and x, it should be called n nu xy. Okay, but we will dispense with that and we'll just call it nu for the materials that we are looking at. Okay, similarly, minus epsilon zz over epsilon xx is also nu, also Poisson's ratio. So that's what we will get. I can write this in a very nice matrix way in the following way: epsilon xx, epsilon, so epsilon yy. So I can start filling it out. I'm going to fill out this matrix. I'm going to write 1 over E here. We'll see if it is correct or not. Minus nu over E, minus nu over E, 0, 0, 0. Let's see if that's correct. So Remember, sigma yy, sigma zz, all of them are 0. So let us multiply this row. Sorry, I should have written this way. Minus nu over E, minus nu over E, 0, 0, 0. And at this stage, we will not worry about all the other terms in the row. It's just the first column. Why is that? Because only this is non-zero. So notice, right now we have, this is the only non-zero term. These things are all 0. So what happens if I multiply the first row by the first column? I will get sigma xx over E. So is that correct? So remember, so if I multiply these two things, I will get epsilon xx is sigma xx over E. So that's correct, because that means sigma xx over epsilon xx equal to E, and that's correct. Okay, so this row times this column will give me that term. Similarly, epsilon yy turns out to be minus nu sigma xx over E. That's what it will tell you. Is that correct? It doesn't look right? Because we said something else. But notice, I can substitute for sigma xx over E and I get epsilon yy is minus nu epsilon xx. So that's correct. I can continue like this. Epsilon zz will be minus nu sigma xx over E, and that's also correct. So all of them will work out. So each experiment will give me one column of this matrix, depending upon which ones I keep 0. So now, before we plunge into the details, I want to talk a little bit about different kinds of Hookean materials. Sorry, let me write it down. Different kinds of Hookean or linear elastic response. I won't say material because it's material response, so I'm being a little bit careful. So different kinds of Hookean or linear elastic material response. So let us say I have a big slab of material, I have a big sheet of material, and I'm going to do many tests, not one test. Notice, one test gives me, roughly speaking, a simple tension test like that will give me one column of my matrix, and I need at least 6 tests to give me the 6 columns of the matrix. Okay, so what I'm going to do is I'm going to cut out samples. So let us say I cut a sample like this, or maybe I cut a sample like this, or maybe I cut a sample like this. So if we cut a sample at a particular location, okay, and response is the same for all orientations of the cut. That means I cut it horizontally, I cut it vertically, whatever I do, I get a sample, then I go and test it. If the response is the same for all cuts, then it is called, then the response is called isotropic. By the way, one word of caution. This depends upon how many tests you do and how accurately you do the tests. So this is not a material property, it is a property of the model, because if I did a crude test, maybe it looks like it doesn't matter which way I cut the sample. But on the other hand, let us say I have a very, very accurate device which gives you very high resolution, then what will happen is maybe it doesn't turn out to be the same in all directions, because in the 10 to the minus 6th place there is a difference. So this is actually a property of how we measure, is a function of how we measure and what we measure. So this is really something to do with the model and not with reality. So if you say, is steel isotropic? The question does not make any sense. We can say, am I going to use an isotropic model for steel? I'm going to treat the response of steel as being isotropic response. Then that's fine. Okay. So most of the things that we talk about are for models only and not for reality. The second kind of thing is, if I take a sample and I cut it in different locations, same orientation, but different locations, and response is the same. This is called homogeneous. So notice, isotropic means same location, different orientations. Homogeneous means same orientation, different locations. So if my sample is cut with the same orientation but at different locations and it turns out to be the response is the same, then it's called homogeneous because it looks the same every location. On the other hand, if for every orientation at a given location it's the same, it's called isotropic. No sense of direction. So for isotropic material, really as far as the response goes, YY, XX, whether it's x-axis, y-axis or z-axis makes no difference. So what we are going to talk about for the material is only homogeneous isotropic response. For such a material response, then we can show that if I did now, let's go back to our matrix, and instead of keeping sigma xx constant, I kept only sigma yy and kept sigma xx, all the other ones 0. Then what I will get is a second row, and that will look like minus nu over e 1 over e minus nu over e 0 0 0. So what it means is that axial stress will not cause the material to change its angles. But this is only true for homogeneous, for isotropic materials, because whether I switch from xx to yy, I'm changing orientation of the sample, it should not matter. Same way if I do zz instead of yy. So I'm doing my third experiment, which is taking a sample along the z axis and applying a force. I will get minus nu over e 1 minus nu over e 1 over e 0 0 0. This is what I will get for a sample along the z direction. Then what I do is I do a shear stress experiment. Now this is very hard to do. In reality, it's extremely hard to do. You have to be very clever to do a shear stress experiment. Unlike simple tension experiments, shear stress experiments are very hard. But if you succeed in doing that, then you will find the next row. So we are now going to move on to I'm going to keep only this one non-zero, all the others 0. And then I'll get the next column. The next column will look like 0 0 0. And I will get what is called the shear modulus. The symbol for shear modulus is either mu or g. This is called shear modulus. 0 0. Then I can cycle my way through, and if you do that, you will get 0 0 0 g or mu 0 0 0 0 g or mu 0. Sorry, 0 g. So I will get 3 constants. The 6 by 6 matrix has only 3 parameters. One is called Young's modulus, one is called Poisson's ratio, other one is called shear modulus, which is g or mu. Either way we have to keep it. These are the 3 numbers. Okay, so let us see which one is which and what they mean. Okay, so this is the key for a thing, for a Hookean material, for an isotropic Hookean material. The compliance matrix has only three parameters, three constants: E, which is Young's modulus, which is ratio between normal stress and axial strain during a tension test. Nu is Poisson's ratio, which is ratio between axial strain and transverse strain. Let us make it clear, negative ratio. During a tension test. So it's how much it thins. So Poisson's ratio will tell you how much it thins. For example, if Poisson's ratio nu is 0, that means pulling it will not make it become thinner. Okay, there are materials like that. One of the materials that is usually cited for this is cork. That's a that's a good material for Poisson's ratio 0. Typically, if Poisson's ratio gets to half, it will turn out that there is not much volume change. We will talk about that in a little bit. So Young's modulus, Poisson's ratio, then we have G or mu is called shear modulus, which is ratio between shear stress and shear strain during a shear test. This is a hard thing to do. I already told you. I'm sorry, I should have been a little bit more careful. And it's not G I will get 1 over mu, 1 over G, like that. Okay, and for strange reasons we don't do 1 over mu, we do 1 over 2 mu, 1 over 2 G. This is just a convenient notation. Okay, so that, remember, we talked about this half business because we wanted to get 6 components of we wanted to get 9 components so that we can write it in matrix form. So that's why there is this half all over the place. Okay, so with that, this particular explanation of what is meant by moduli is done.